Hi and welcome to Data Science for Economics. This part is dedicated to prediction models. We often talk about population and we talk about samples from that population. When we talk about population of interest, we think about data generating process, something that generates a variable of our interest from some function f. When we talk about samples, we talk about random samples from that data generating process, such that this sample follows the general distribution from the population. So for example, when we talked about different heights of Vienna musicians, we had in mind a certain population with certain distribution of heights in that population. And when we talk about samples, we could draw 4 different samples of 20 observations each, and each time we will get some certain variation in the average, which will be around the true population mean. In general, we can also talk about a distribution of y, a data generating process where y depends on x. And what can be simpler than y equal x plus some noise? So we have this 45-degree conditional expectation function and plus some noise epsilon around every single point. So the data would be distributed something like this, along the 45-degree line and then some certain variation around this line. Now, suppose we draw a sample from this population data generating process. So these 4 observations. If we want to predict y from x, there is nothing better for us to know than the true data generating process. Now, we don't know the true data generating process. We only observe a sample from that data generating process. But the problem is that the same sample could have been generated by other data generating process. So we have to infer about this distribution in the population from the observations in our sample. So how do we approximate the data generating process? Again, we want to approximate it because the true data generating process is the best prediction model. For example, given the sample, we can approximate the DGP by a simple straight line or OLS with 2 parameters, alpha and beta. Or we can also fit a higher order polynomial, for example, this kind of OLS regression, which will basically fit our 4 observations perfectly. Now we have 2 candidates. Candidate 1, a straight line, or candidate 2, this higher order polynomial candidate. Now, which one is better? We don't know. We don't know the true data generating process. But fortunately, we have another independent random sample from the same data generating process. So we can basically ask, which of the 2 candidates are going to do better at prediction? Let's do a horse race between the 2 models. So we will call this a validation sample, and the previous one we called a training sample. So this is a training sample and this is a validation sample. Now, this is our candidate 1, this is our candidate 2. We are going to put the validation sample and we are going to ask ourselves where the prediction errors are smaller, when we use candidate 1 model or when we use candidate 2 model. Now, those red lines are prediction errors, and clearly candidate 1 is better than candidate 2. So if we calculate the mean squared error for both candidates on the new sample, candidate 1 will have lower mean squared errors. Now, the final step we do is we want to know how good the chosen model candidate 1 does in general for new prediction tasks. So for this, we will get yet another sample, which we will call test sample, completely untouched by training or validation cycle. And using this new sample, we will estimate the prediction errors, the mean squared errors here. And this will be our expected prediction errors produced by this model. So in general, all prediction tasks have the same basic steps. Step 1, train a less flexible model on a training sample. Step 2, train a more flexible model on the training sample. Now you can have not just 2, many different models vary in their flexibility, but just for conciseness, we just keep it here 2. Now, after you're done training different models, step number 3 is to compare mean squared errors on the validation sample. And at this step, you choose the one with the smallest mean squared errors. Now you calculate mean squared error of the chosen model on the test sample, and the square root of the mean squared error that you calculate here would be the expected prediction error of your best prediction model. That's it. All models will look exactly the same.